Welcome to the fourth lesson. Today we shall be analyzing systems. Some of the systems that we have considered are a simple circuit, a mass spring system, and a car moving towards the right with a constant speed. Before we begin, I would like to advise you to pause the video whenever I ask you to. In that pause time, I would ask you to solve some questions. Those questions are part of your learning engagement. If you do so, then by reaching the end of the video, you would have done all the questions of your learning engagement. Let's begin. The following tables show data that we collected on the four systems. The variables are current and voltage, extension and mass, distance and time, and y and x coordinates. Independent variables are those variables of a system that we change. They are not affected by other variables. The variables that change because of the change in independent variables are called dependent variables. The main focus of today's lecture, however, is finding a relation between variables and telling whether or not the two variables are proportional. Let's begin with the first system, that is current and voltage system in a circuit. Some values are given in the table from the experiment conducted. These values can be written in the form of ratios. From our previous lessons, we can see that all these ratios are equivalent. Therefore, when we write them in the fraction form, we put an equal sign between them. We have some unknown quantities as well. We name them x and y. To find the value of x, we can equate it with any ratio in the series, since all the ratios are equivalent. We can find the value of x pretty easily. We can do the same for y. We can equate it with any other ratio in the series since all the ratios are equivalent. We can find the value of y again. You can see how equivalent ratios can help us find the unknown quantities. Now we shall look at a method of finding whether two variables are proportional to each other or not, just by looking at the table. We already know that all these ratios are equivalent, and we also know that if voltage in the circuit is made 0, then the current in the circuit would also become 0. This means making one variable 0 makes the other one 0 as well. Therefore, there are two conditions that tell us whether two variables are proportional or not. Number 1. All the ratios in the table must be equivalent, which means that we should be able to simplify them all to one simple ratio. The second condition is that when one variable is made 0, then the other one also becomes 0. We now understand how to find whether two variables are proportional just by looking at the tables. When these two conditions are met, the two variables are said to be proportional. They can be written as dependent variable is proportional to independent variable. In this case, current is proportional to voltage. The mass spring system also meets these conditions. The moving car system also does, although the values in the moving car system table are not correct as of yet. I shall correct them in the course of the lesson. We have now achieved proportionalities for all four systems. There is, however, one more tiny step to go before we can make use of these proportionalities, and that is converting these proportionalities into equations. We shall replace the proportionality sign with an equal to sign. To create an equation from a proportionality, we have to replace the proportionality sign with an equal to sign and a constant. We shall do that with all the proportionalities, replacing the proportional sign with an equal sign and a constant, C. Congratulations! You have just made equations for 4 systems. However, what are the values of these constants? Let's find them. We shall rearrange these equations so that we can find the value of these constants. Let's begin with the first one. In order to find the value of C, we have to use the values of current and voltage from the table. Since all the ratios are equivalent, simplifying them gives us one same answer, that is 5. So the constant in this case is 5. Let's move on to the next example. We take the values of extension and the mass from the table and we simplify the ratios and we get 4 by 25. Moving on to the next one, we use the values of distance and time from the table. All the ratios are equivalent, so simplifying them gives us one constant answer, that is 25. Try to find the value of constant in the last example as part of your learning engagement. Pause the video now. At this stage, it is natural for us to ask that why did we find the constants? What benefit does it give us? Let's find the benefits. We can see that in these tables there are certain values that are unknown. The constant C helps us find those unknowns. In the case of current and voltage, let's find the amount of current for 6 volts. We put the value of 6 under V and put the value of constant and we get the answer 30. Moving on to the next unknown, we put 9 in the value of volts, 5 for the constant, and our answer is 45. As part of your learning engagement, find the unknowns in the other 3 systems. Pause the video now. Let us now study how we can identify proportionality between 2 variables just by looking at their graph. Let's take the example of the current and voltage system. We shall plot the current on the y-axis and the voltage on the x-axis. The data is given in the table, and we shall plot only one point manually. The rest of the points, we shall plot them in a graphing calculator. The first point is 1.5 volts on x-axis and 7.5 milliamperes on y-axis. We join the lines and make a dot. However, this is not so accurate. Let's move on to Desmos. We plot the voltage on x-axis and the current on the y-axis. We now join all 3 points and we get a straight line that passes through the origin. Origin means the 0, 0 point. We can see that the first condition of the line passing through the 0, 0 point is satisfied. We can also see that the second condition of the line being straight is also being fulfilled. These are the two conditions that, when fulfilled, mean that both the variables are proportional. Let's move on to our mass spring system, in which there are two variables, extension x and mass m. We remember we had a confusion of choosing 40 centimeters over 41 centimeters when we measured the extension of 250 gram mass. For your satisfaction, I'll take 41 centimeter, which was the actual reading, and we'll see the difference between 40 and 41 centimeters. We plot the mass on x-axis and the extension on the y-axis. At this point, I shall make another point on the graph that is 250 grams and 40 centimeters, and we will see how much that changes our system. You can see that the difference between 40 and 41 centimeter is very small. Let's pass a line through all the 3 points. We can see that the line is passing through the origin. And we can also see that the 40 and 41 centimeters are indistinguishable. In mathematics, sometimes we make a small trade-off between accuracy and ease of doing calculation. Theoretically, the extension for 250 grams should have been 40 centimeters, but in practical systems, we have room for small errors, although they do not really change our entire system. The line passes through origin and satisfies the first condition of proportionality. And the line is a straight line as well, which is the second condition of proportionality. This means that extension and mass are proportional. Plot the graph using the data of moving car system and the straight line using Desmos as part of your learning engagement. Pause the video now. We can now identify proportionality between two variables from a table and a graph. Let's do the same for an equation. In an equation, if one of the variables is assigned a 0 value, then the other variable also becomes 0. The second condition for an equation is that both variables should be raised to the power of 1 only. The power of x is 1 and m is 1. If it is otherwise, then the variables in the equation are not proportional. Let's see why that is. We shall take the case of y equals cx as a case. Let's plot y equals cx. The c is the slope of the line. If you increase it, the slope changes. Let's add another equation, an equation that does not have 1 as the power of its variables. You see, as soon as we change the power from 1 to 2 and 3, the line stops being straight, which is a condition for proportionality. We can now identify proportionality between variables from a table, a graph, and equation. Let's summarize. What makes a relation a proportional relationship? The equation of a proportional relationship always has the form of y equals kx, where k is called the constant of proportionality. The table of a proportional relationship can be recognized by the fact that the y-coordinate dependent variable is always the same multiple of the x-coordinate, the independent variable. In this case, it's 3. We multiply 3 with the independent variable to get the dependent variable. Does the proportional relationship have to include the point 0, 0? Yes. A proportional relation can be represented using a graph, and that graph always passes through the 0, 0 point. A ratio is a way to compare different quantities. A ratio can be identified in the following forms. Ratios can be simplified as well. Equivalent ratios are useful in solving unknown quantities. A proportional relationship can be represented using a graph, a table, and an equation. Proportional relationships exist when one variable can be obtained by multiplying the other by a constant of proportionality. We have achieved our objectives for this lesson. Thank you for watching.